Hello, welcome to this video episode of FCH 511, Atmospheric Chemistry. In this episode, we're going to be discussing the Arrhenius expression and how to use it not just to calculate rate constants, but also in connection with thermodynamics. One of the important things we'll be doing is looking at a standard reference source for atmospheric chemical kinetics data and how it presents the data and how to use that data and what some of it means. All right, on the screen we have the Arrhenius expression. The rate constant is equal to a pre-exponential term multiplied by an exponential term. The pre-exponential term, symbolized by A, is called, with some imagination, the Arrhenius pre-exponential term, or for short, the A factor, and that's how it's listed in the reference work, as you'll see. E subscript A is the activation energy. E for energy, subscript A for activation. It's important to note that this is approximate, it's not universal, and it's not a law of nature. But it's very useful. So, with the Arrhenius expression, there are some issues of units. We have the gas constant R in that exponential, and that can be listed in calories per mole Kelvin or joules per mole Kelvin. The activation energy is most commonly listed in kilocalories per mole or kilojoules per mole. And when it's listed like that, you have to remember to convert kilocalories to calories or kilojoules to joules. Otherwise, you'll have an error of a factor of 1,000 in the exponential, and that will be a big error. To avoid this sort of problem, the reference source that we use lists the activation energy divided by R. And that is a quantity that has units of Kelvin. And that avoids units problems, since in this context our temperature is always in Kelvin. So in this bottom equation is related to how is the Arrhenius expression in the format that it's implicitly used in the data reference, where the activation energy is already divided by R. So that's in Kelvin, the temperature is in Kelvin, so the units are taken care of. That saves a lot of problems. So let's look at the one section of this data value, this reference source. I call it Sander for short because Stanley P. Sander is the first of several authors. Its official name is JPL Data Evaluation 10-6, which is why we call it Sander. So here's a section of Table 1, which has rate constants for bimolecular reactions. First column lists the reaction. The second column lists the A factor, the pre-exponential term. The second column lists, it's written as E over R. That's really the activation energy divided by R, as we talked about. So this E is the activation energy. So this number here has units of Kelvin. The next column lists the rate constant room temperature. So if we look at this A factor and this EA over R, that means we write the Arrhenius expression as in this equation, 2.6 times 10 to the minus 12 multiplied by exponential of minus 1,420 divided by the temperature in Kelvin. So at 298 K, if we plug that in, we get a value of 2.2 times 10 to the minus 14. Since these are all bimolecular reactions in Table 1, the units are as follows: cubic centimeters per molecule second. Now it's convenient that we can do the calculation ourselves and compare it to the room temperature value listed in the table. This is a way of checking that you haven't made an error. We can plug in any temperature we want. If we plug in 225 Kelvin, a much lower temperature that's still very atmospherically relevant, then we get a lower rate constant, about 5 times lower, 4.7 times 10 to the minus 15, with the same units. A brief note about significant figures. The Arrhenius pre-exponential factor here is always listed with at most 2 significant figures. So we keep 2 significant figures when we report rate constants here. This work by Sander and et al. has additional information. So here's the same reaction, same A factor. This shows the whole page. It has 3 more columns. The F at 298K is the uncertainty at room temperature. So 1.1, if you multiply this by the room temperature rate constant by 1.1 or divide it by 1.1, you'll get their estimate of how uncertain the room temperature rate constant is. This is explained in more detail in the introduction to Table 1. The G gives the uncertainty in the Arrhenius pre-exponential factor. In this course, we won't be using them for calculations, but it's handy to know that there are error estimates on these numbers. And then the last column, there are notes, and these are actually hyperlinked. So if you want to find out the basis of the recommendation, why they think it's certain or uncertain, what data they used or didn't use, and it includes all the references to the primary literature, you can do that. Let's look at another reaction that appears on the same page. Here, a reaction between 2 radicals, CF3O2 and NO. We again have the A factor, and we have the activation energy divided by R, but here we have a negative sign in front. So the Arrhenius expression for this is shown here, 5.4 times 10 to the minus 12, and E to the minus the activation energy over R. Here, in this case, the active energy over R is negative. So you have negative, negative, which means you have positive. So the exponential term is actually positive. And at 298K, we get a rate constant of 1.6 times 10 to the minus 11, just as in the 4th column of this table. Interesting, this rate constant at 298K is higher than the Arrhenius pre-exponential term. And if we go to lower temperature than room temperature, the rate constant gets even higher. Okay? When you have this negative activation energy, the rate constant will go up as the temperature goes down. This is not the usual situation in kinetics. It's rather common in reactions between 2 radicals, especially, well, very importantly, when NO is one of those radicals. So you have to pay attention and look for this minus sign, because if you don't include that in this expression, you will be off by a factor of about 6 in the rate constant. Here's, from the same page, another couple of reactions where they don't list an A factor and they don't list an activation energy. What they list is an upper limit to the rate constant. So at room temperature, they say the rate constant is less than 3 times 10 to the minus 15 in this case, and in this case, less than 5 times 10 to the minus 16. What this means is that there's experimental data in which they didn't succeed in measuring the rate constant, but they were able to determine that it was slower than a certain value. If it was faster, they would have been able to measure it. When it comes to calculations, this gives us some uncertainty. Should you use this number? You may want to if you think the reaction might be important. However, while we know the rate constant is not higher than this value, we don't know how much lower the rate constant is than this value listed. It could be many orders of magnitude slower than the value listed. And if you use this number in a calculation, you may in fact be overestimating the importance of the reaction by an order of magnitude or a factor of a million or more. So most of the time, if we have an upper limit, the reaction isn't important enough to matter. And if you do the calculation with this number, you'll probably find that out. When I say unimportant under atmospheric conditions, very probably. And in the lab, when they were trying to measure this rate constant, and they could play with the conditions, they weren't able to see reaction. So this means the reaction is probably unimportant. Okay. One final example from Sander. You have reactions that will have M over the reaction arrow, and rather than having any data, the first column will say see Table 2-1. Table 2 has rate constants for termolecular reactions, reactions where there's a third body, that is another molecule of nitrogen or oxygen needs to enter into the reaction to have the reaction move forward. We'll be talking about these later in the class. For now, if you need a rate constant for a reaction like this, I will give you a value that's appropriate to that pressure and temperature that you're working at. Because of the need for involvement of another molecule of gas that doesn't react but participates, these rate constants for these reactions depend on the pressure as well as the temperature. As I said, more details will come later. Let's talk now about the physical basis of an activation energy. Here is a reaction coordinate diagram, as you may have seen in organic chemistry. We have an energy axis, which we can associate, in fact, with the enthalpy. Here is reactants going to products over a transition state. Okay? The reactant has to have enough energy to reach the transition state, and so this difference in energy between the transition state and the reactant is associated with the activation energy. And so if we know what that activation energy is from theory, we can plug that in to an Arrhenius calculation. Alternatively, if experimentally we've derived an activation energy, one could know that what the energy of the transition state is relative to that of the reactants. So there's a lot one can do with this. In the context of this course, it's handy to get upper limits to rate constants. So this applies to endothermic reactions where the products are higher in enthalpy than the reactants. So consider a case where you know the enthalpy of reaction is positive, but you don't know the activation energy. The transition state has to lie above both products and reactants. It could be a lot above, it could be just a little above, but at least has to be higher than the energy of the products. And if we have numbers for this, then we can use them. So here I put some numbers on this reaction coordinate diagram, the enthalpy in kilocalories per mole from 0 to 20. And we have reactants, products, and we're set for this example that the enthalpy of reaction is plus 14 kcal per mole. The transition state will lie at least 14 kcal per mole above reactants, maybe a lot more. What this means is that we have an upper limit, a lower limit to the activation energy. It must be greater than the enthalpy of reaction, which is plus 14 kcal per mole. And using R in calories per mole, we can say that the activation energy is greater than 7,046 Kelvin multiplied by R. We can then use that in an Arrhenius expression for the rate constant. So, if we want an upper limit to a rate constant for a bimolecular reaction, say the rate constant is less than some maximum value of this Arrhenius pre-exponential factor, multiplied by e to the minus this lower limit to the activation energy that we calculated on the previous page, 746 Kelvin times R. Now, there's an exercise in class where you'll get an estimate of the maximum value of the Arrhenius pre-exponential term. It's roughly 10 to the minus 10 cubic centimeters per molecule second for bimolecular reactions. So for a bimolecular reaction, we can say the rate constant is less than 10 to the minus 10 multiplied by the exponential term. So using the value we derived from the endothermicity of reaction to get a lower limit of the activation energy at 298 K, we can say that the rate constant for this reaction is less than about 5 times 10 to the minus 21 cubic centimeters per molecule per second. Now, the highest rate constants we see are about 10 to the minus 10 cubic centimeters per molecule second. So this rate constant is more than a factor of 10 to the 10 smaller than the maximum value. This means this reaction has a very low rate constant. It's probably unimportant, and that's because the activation energy was as high as it is, in this case 14 kilocalories per mole. When it comes to unimolecular reactions, we have, we can get at upper limits as well, but we can also get at rough estimates. So the Arrhenius pre-exponential factor for unimolecular reactions is typically within this broad range of 10 to the plus 11 to 10 to the plus 17 in units of seconds to the minus 1. Remember, this is a unimolecular reaction, so these are the units, unlike the units of the bimolecular reaction. So if we use this, equate the Arrhenius expression with these range of A values and our same 14 kcal per mole activation energy, you can put some range on the rate constant. It has to be less than about 5 times 10 to the 6 per second, but it's probably greater than 5 per second. And this is helpful data. All right. That is all for this segment of FCH 511, Atmospheric Chemistry. Thanks for joining us. I'll see you next time.